levels of sophistication, all right? This is going to be fairly sophisticated. So imagine that I have two blocks. We'll call this mass 1, and they're connected by a string over a pulley. Let me draw my pulley a little bit bigger. And we'll say that M2 is hanging over the side, all right? So they're connected by string, and the string is hung over a pulley. And I'm holding, well, let's say I'm holding M1, all right? So that everything is at rest. If I let M1 go, common sense tells us that M2 is going to be pulled downward and M1 is going to be accelerated this way. What is the overall acceleration of this system going to be? So now we actually have to find an equation that will allow us to calculate the acceleration of the entire system, right? Now, first things first, let's note something. If M2 is accelerating downward this way and it's pulling M1 this way, then the accelerations are going to be the same, all right? They must be accelerating at the same rate because they're attached to the same string. Next note, all right? We can say that M2 is going to have tension in it upward, and M1 has tension this way, and because the tensions are exerted by the same string, the tensions at each end are going to be the same, all right? So we want to make those preliminary remarks before we get going. Now, let's draw a free body diagram for M2. If I denote a dot on M2, what forces are acting on M2? Well, I have no horizontal forces. Everything is in the vertical direction. And so we know that the downward force of gravity is acting, and there's an upward force of tension, but this object is still going to be falling, so the arrow of gravity is going to be larger. Now, what about M1? So M1 actually only has one force acting on him. This won't be true when we get to friction, but we're going to assume that he's sliding across a frictionless surface. So he's only going to have one, I should make him the same length as the other arrow. One force acting on him, and that's going to be tension. All right, so now I need a robust coordinate system in both the vertical and the horizontal directions. So I'm going to call this plus x and this plus y, all right? Now, let's look at F equals ma for both objects. Let's look at M1 first. So if I look at F equals ma for object 1, there's only one force acting on it, T. So the force on object 1 is going to equal T, and that will equal the mass of object 1 times A. Now, the force on object 2, the net force on object 2, is going to be the tension acting upward minus the force of gravity, since gravity is acting downward, and the overall acceleration is going to be downward because the object's going to be falling, so this is going to be equal to negative ma. The negative sign comes into play because A is downward in the negative y direction, all right? So now, we actually have two unknowns and we have two equations. We don't know what the tension is, and we are looking for A. So what I'm going to do, I already have this equation solved for tension, so I'm going to plug this value in for right here, and that will allow us to solve for A. So this is going to give me M1A minus Mg equals, and this should be M2's, all right? M2A, negative M2A, right? So now what I want to do, I can move this term over here and this term over here. I'm going to get M1A plus M2A is equal to M2G. So the total acceleration that, or I should say the total force on this object and this object must equal the force of gravity, since the force of gravity is supplying the force that's causing it to move downward, accelerate downward. That's the force that's modifying the tension here in the ropes. So the sum of the two net forces must equal the force of gravity, all right? And so what I can do is factor out my A, and A times M1 plus M2 is going to equal M2G. And so then A, I'll write it over here so it's not getting too low. So then A is going to equal M2G divided by the sum of my masses, right? And let's make sure this formula makes some sense. What if M1 is really large compared to M2? How's the acceleration going to look? Well, the acceleration shouldn't be very high compared to G, because if M1 is very large, then it's going to dominate this denominator, and the larger you divide things by, the smaller your overall result. What if M1 is really, really small compared to M2? Okay? If M2 is very large compared to M1, then it really shouldn't feel the effect of being attached to M1, so the acceleration downward should approach that of gravity. Well, if M2 is really, really large, then the denominator here starts to approach M2 itself, and I get M2 divided by M2, and my acceleration is approximately the acceleration due to gravity. So this formula is consistent with what we would think would happen, but this is mathematically one way that you can get there, okay? Now we're going to see several more examples